Reinforcement learning is very powerful. It allows an AI agent to interact with an environment by learning an optimal policy. As we learned previously in the introduction to reinforcement learning, the three major parameters in reinforcement learning are the environment states, or the possible configurations of the environment, the agent's actions, the possible actions to take in a given environment state, and the agent's rewards. The goal of the agent is to maximize its cumulative reward. The optimal policy tells the agent what is the best action to take in a given environment state to maximize its rewards. If you haven't already, click the subscribe button below and let's get started. So today we will learn how to use powerful Monte Carlo methods, in other words, random policies, to create an agent that learns to play the game of blackjack. We will use OpenAI's GIM for the technical implementation. Started by technical founders Elon Musk and Sam Altman, OpenAI is a research organization specializing in reinforcement learning. So first here we'll do some imports here. So we'll import sys system. So you'll see in a moment why we need that, and then we'll import GIM. So that's OpenAI's GIM, the platform for reinforcement learning. We'll import NumPy, SNP, and from collections we'll import the default dict. You'll see why we need dictionaries, the default dictionaries as well. And then we're also going to plot some helper functions here for plotting our policies and our state action value functions. So first of all, here we're going to create an environment, a blackjack environment for the game of blackjack, and so we're going to call GIM and .make. So call the make function. We'll just pass the string here for the blackjack v0 environment, so that we have an object here which is an instance of this blackjack environment. So here, so first of all, blackjack, here we have the source code here, the blackjack.py from OpenAI GIM. So the game of blackjack is a card game, of course. So where the goal is to obtain cards to sum to as near as possible to 21 without going over, and you're playing against a fixed dealer. So you have face cards that are worth 10 points, and then you have aces, an ace that can count either as an 11 or as a 1. And it's called usable at 11. So depending on your current count and your hand, you can choose your ace to be 1 or 11. And so, okay, so what are the states here? The states of the environment, what are the actions? So the states is a 3-tuple, so there are tuples of the player's current sum, which can take on values from 0 to 31. 31 will be the maximum overshooting. In 0, there's really nothing. And then the dealer's face-up card. So the dealer here that you're playing against has one face-up card and one face-down card. So once you're done with your cards, so you're good to go, the dealer flips the other card. And then the dealer actually has to keep drawing cards until it has at least 17, and the dealer can overshoot. So if the dealer overshoots, you win no matter what. And then if you overshoot, you automatically lose, independent of the dealer. So the state is the 3-tuple of, okay, so the player's current sum, the dealer's face-up card, and then whether or not the player has a usable ace. So whether or not your ace can still count as an 11, as a 1, or as an 11. So that's the state space. Those are the states of this environment, blackjack environment. And now the actions, there's only 2 possible actions in this environment. So the agent can either stick, which means it doesn't want to draw any further cards, just want to complete the game here. And hit, which means it wants to draw another card. And stick, it's a 0, and then hit is a 1. So just 2 actions. So here, if we actually print from our environment object here, if we print the observation space and the action space, here we see that for our observations we have our 3-tuple, and it's a discrete distribution of 32 possible values, because 0 counts, 0 to 31. And then for the dealer's face-up card, it's a discrete distribution of 11 possible values. So the maximum number will be 11 there for the face-up card for the dealer. And then whether or not the player has a usable ace is just a discrete distribution of 2 values, yes or no, 0 or 1. So that's our observation space. And now we also have our action space, and it's just a discrete distribution of 2 values, stick or hit, 0 or 1. So that's very simple. And by the way, I'll put a link to this, to blackjack.py, in the description, so you can look at this at your own leisure and see how this is working. But it's basically just a coding implementation of the game of blackjack, particularly in this context of reinforcement learning. Okay, so here we are going to to use a random policy, what we call a Monte Carlo methods. So why would we? So and you'll see why using a random policy, using random policies, can actually give you an optimal policy in a very powerful way of deciding what actions to take in a given environment state. Here in the case of blackjack, by executing random policies and collecting episodes, thousands or hundreds of thousands or even more episodes, and just getting statistical values, statistically significant values, just from doing random policies, and you'll see how that works. So it's very, very powerful. So here we'll just do a quick example here with 3 episodes. So we'll run our random policy or Monte Carlo algorithm for just 3 episodes. So for I_episode in the range of 3. So first of all, we'll create a state variable here, and we'll just go ahead and call the reset method on our environment object. So that's just so we have a clean environment and reset environment. And our environment starts with the dealer. Again, dealer has a face-up card and a face-down card, and then your sum. So you have also a face-up card and a face-down card. So when you start the environment, you have 2 cards, essentially. So we're just going to loop through here, and we'll just say while true because we just wanted the conditions to stopping the loop are within here. So we just want to go through it, and we'll go ahead and print the initial state of the environment for just 3 episodes, and let's see what we have. So we'll go ahead and print the state, which again is the current sum of the player, and for the cards that it has, the face-up card of the dealer, and whether or not there's a usable ace. Okay, so then we'll create an action variable here. So we'll go ahead and call environment.actionspace.sample, and you'll see here in the blackjack.py Python script, you'll see how that's implemented. But you're basically random sampling from the action space, which is either 0 or 1. So whether to grab a card or not grab a card. Okay, so we have that particular action. And now we're just going to print that action. So if it's 0, it's stick. Otherwise, if it's 1, it's just hit. So we want another card, or we don't want a card if it's stick. So we'll here assign. So we have 4 variables: the state, the reward, whether we're done, whether we reach the terminal state, and the episode has concluded, and info here. So we'll call environment.step function here, and a step method in our environment object, and we just pass in that action. So we'll take a step in that environment to take that action, and then we'll get a new state, we'll get a reward, and then we'll know whether we're done or not here, and then some additional information if we need it. So if we are actually done, we'll go ahead and print that's the end of the game, print the reward that we actually got, and if you won, if the reward is greater than 0, otherwise print that we lost. So here the rewards, the way they work is if the player wins the game, if the agent wins the game, the reward is 1. If the agent loses the game, the reward is -1. And then if it's a draw, it's a 0. So here, we'll see for the first episode, the initial state was 21. Well, it just happened to be 21 with those 2 initial cards for the player. And the face-up card of the dealer was 10. And then we had a usable ace here. So in this case, for this 21, 11 of those was an ace. So it had an ace and either a 10 or a face card. And then the random action taken by the agent here, by this random policy, essentially, it's a stick, which means do not draw a card, which is a great decision. You're already at 21, and the reward is 1. It's the end of the game. The reward is 1, and the agent won this particular game. Okay, that's great. So let's loop through the next one. The initial cards, the 2 cards, added up to 7. Okay, the dealer had a 10 face-up card, and then there's no useful ace. Okay. So then the agent decided to stick. It's a random policy, or just random sampling from the action space. So he decided to stick. Okay, there's a high chance that you will lose. And in this case, you'll definitely lose here in this case if you stick with 7, because the dealer had a 10. So that's the end of the game. The reward is -1 because the agent lost the game. And then for the third episode here, we started with 11. For the two cards of the player added up to 11. Okay, the dealer had a 5 face-up card, and then falls no usable ace for the player, for the agent here. And the agent decided to stick. Again, it's a random policy, so random sampling from the action space. So it's stick. Okay, so we're not going to draw a card. And now what's the result? the agent 1 received the reward of 1, and it won. So how is that possible? So the rules of the blackjack environment here, the dealer has to actually grab cards until it has at least 17 as a sum of the cards. So the agent must have actually, or not, the dealer must have drawn cards to the point that are actually overshoot. So from 21. So because that was the case here in this particular case, the agent won. So it's very interesting to see. And then later, as we go through this implementation, we'll be recording all of the particular actions taken in the particular environment states and the corresponding rewards, and we'll create an optimal policy from that. So here we're getting to our Monte Carlo prediction here. So we run an implementation, and we're going to estimate the action value function. So from the introduction to reinforcement learning, we saw that we want to create, by going through many different episodes, collect a queued table, basically create a queued table. So put it in a table, put the actions and the rewards. So you're in a particular state. So you're in a particular state of the environment. The agent took a particular action in that state and received a particular reward. And we want to keep track of all that in a table that we call the queued table. And that queued table is an approximation of the action value function. So the actions to take in the action to take in a given environment state, and get a reward from that. So the more episodes, the more times we loop through that, we go through that, we're getting closer and closer to finding that action value function. And then we use the action value function for finding the optimal policy. So in this case, we'll investigate a policy where the player, so the agent in this case, almost always sticks if the sum of the cards exceeds 18. Which is reasonable, which, why not? If the sum exceeds 18, then you don't want to draw another card. The probability of overshooting 21 is very likely, so we want to stick. So we set the action stick with 80% probability if the sum is greater than 18. Now we want to pick, grab a card with 20% probability in this case, because there is actually a smaller chance. There's a chance, smaller, but there's a chance that you won't overshoot. That your sum will still be 20 between 18 and 21. And so if the sum is 18 or below, we want to select the action hit, so draw a card with 80% probability, and then the other action with 20% probability. So we'll write a function that will sample an episode using this policy. It's a Monte Carlo method. Now, so the function will accept as input as its parameter an instance of the OpenAI gym, the Blackjack environment from the OpenAI gym, which we already have. And then as an output, it will return an episode. And an episode is a list of state, action, reward tuples, and corresponds to the collection of all these state, action, rewards, and so on until the final time step, so reaching the terminal state when the episode ends. So the episode at I, at any index I, returns a particular state, action, rewards tuple, and then if you index each one of those, you'll grab those particular values. So the state, the specific action, and the specific reward. So let's look at our function here. So we call it generate episode from limit stochastic. So it's a Monte Carlo method here. That's how we're going to generate our episode, the random policy. So we'll accept an instance of our Blackjack environment, and we'll initialize an episode to an empty list here, and we'll also reset our environment state, our Blackjack environment, as we did before. So we have a clean state every time that we're going to draw an episode, generate an episode, and we just call Blackjack environment dot reset method there. Okay. So again, we'll just do a while true here, just a loop, and the conditions for ending the loop are within it. So first of all, we'll create our probabilities. So basically, as we said before, if the state at 0, so basically the state at 0 corresponds to the player's current sum. So if the current sum of the player is greater than 18, then we want to stick. So now draw a card with 80% probability and draw a card with 20%. So we have the list, and you'll see how we'll use it in just a moment. And then otherwise, so if the state is not that, so there's only two possibilities. So just otherwise, we want to just flip it. So we want to actually stick with 20% probability and draw with 80% if the sum of the cards is less than 18, as we saw before. So now we'll create an action variable here. So we'll use numpy here. So np.random.choice. And then, so we're going to grab two values here. So np numpy.arange 2. So we're just going to get 0 and 1. So those correspond to the two possible actions. And then for each one of those, we want to assign the probabilities here. For the second parameter p, the probabilities, we assign these probabilities. So for sticking, in this case, we assign 80%, and for hit, so drawing a card, 20% if the state at 0. So if the player's current sum is greater than 18, and otherwise, the other option. So that's our action here. Each action has a probability. Each action 0 or 1 has a probability based on the state there. Okay, so we're actually going to go ahead and call take a step in our Blackjack environment and passing in the action here. So whatever our action happens to be here, we want to take a step in that environment. So take that action. So now we're going to get a new state, right? The next state for the environment. And then we're going to get a reward, either -1, 1, or 0. And whether we're done or not, and then info. Okay? So now for our episode, now that we have here, we're going to append these values. So we're going to append the state. And by the way, here, we're not appending the next state. For this episode in particular, we're appending the actual state that we started with. So we get here, when we step in the environment, we get in the environment, we get the next state. But for this episode, we want the state corresponding to this episode. So that was before getting the next state. So that's the state. We have the action that we took in that state, right? Again, before the next state. So state action, and then the reward that we got for having taken that action in the particular state. So that is our episode, and we're appending it to our list here. And then we just reset our state now to the next state, because now we're getting ready for the next one. So if we're done, if this return true, we're done there, then we just break from this loop and return the episode. So that's our function that we'll use to generate episodes. Okay. So now we'll just go ahead and test it real quick. So we'll loop through for I in the range of 3, so 3 episodes. We'll just go ahead and print that function, passing in our environment that we created previously. And as you can see here, we have the current sum of the player, the dealer's face-up cards, whether we have a usable ace, so that's a 3 tuple. And then here, so we have the action that we took in this particular state, and then the reward. So in this particular case, the action was hit. So we were at 17. And in that case, we took this action 1, which is hit. So we draw another card, and we probably overshoot here, so we lose. We lose the game because we went over 21. Same here. So we have 16. Then we have 4 here for the dealer's face-up cards. We do have a usable ace, and here we say stick here. So we actually didn't draw a card. We stayed with the 16, and we won. So which means the dealer probably overshoots here. I keep drawing cards. Overshoots 21, and then for the last one we have 11, and then 5 for the dealer. No usable ace, and then we decided to draw a card. Okay. Then we draw a card again. So now we are at 14 for the next state here. So because we're still not over 18, we still have a probability of drawing a card. So we go ahead and draw a card, and in this case we lost the game. So we probably overshoot from 21. So the dealer wins. So that's just an example of this function. What it's doing, what it's returning when it returns here. So it returns the episode. Okay. So now we'll go ahead and do it for many more episodes, and you'll see now how we're going to do this implementation. So we're going to create a function here that we call it Monte Carlo MC prediction.q. So our purpose here is to return our Q table, which is an approximation of our action value function. So our algorithm here, now we can implement either first visit or every visit Monte Carlo prediction. What that means is that, so for if the agent's in a given state, sees a given state, and then takes a given action, then it gets a reward, right? Now, what if we come across that pair again, the same state and the same action again later? So do we want to take into account only the first visit to state action pair, or take the every visit and just average out the rewards or the return. The cumulative reward is what we call the return at every visit. So in the case of blackjack, the techniques are equivalent, but it's something to know that in general it would matter whether you considered either first visit to that state action pair or every visit, and you average out all of them. So in this case, our algorithm, our function, will have three arguments. So of course the environment, an instance of our OpenAI gym environment, the number of episodes, so how many episodes do you want to loop through, so how many episodes you want to generate. And the more you have, the more of an accurate of a policy you're going to end up having, and the better of an approximation to the action value function you'll have. And now we have a generate episode. It's a function that returns an episode, which we wrote here. This function, so we're going to pass that so we can generate episodes. Okay, and then the last one is the fourth parameter here for our function is gamma, and this is called the discount rate. So the discount rate, so here's the thing. When considering an agent interacting with an environment and getting rewards, which rewards are more important? Would you say that the immediate rewards in the more immediate future, or rewards in the distant future? Because the agent, we wanted to maximize cumulative reward over all time steps. So not only the immediate reward, but also rewards coming in the future. We want to maximize the rewards that we get for the future. But which one is more important? Rewards that you're going to get immediately or in the far distant future? Now, in terms of probability and statistics, it's just easier to predict the more likely that we'll get rewards in the near future than trying to predict something in the distant future. So the gamma here, this parameter, the discount rate, gives more of a weight, more of an importance to current rewards that come immediately in the future than the ones that come after. In general, it's a value between 0 and 1. Now, if the value of gamma is 1, then all of the rewards are the same. So you care equally about the next ones coming in the near future than in the far future. Okay, and this is a hyperparameter that you can tune. And then 0 means you only care about the next reward and nothing else. And you'll see how, and then you usually want a value between 0 and 1 in practice. So you have a balance between immediate reward and future reward, because the goal of the agent is to maximize its expected cumulative reward over all time steps. You'll see how that's implemented here in our algorithm. And then the return value for our algorithm is the Q table, which is an approximation of our action value function. And that is this is a dictionary. This Q table is a dictionary of one-dimensional arrays, and the dictionary is the state, action, and then the reward, the return rather, the cumulative reward or the return for that for that action in that particular state. So let's go ahead and create our function here. So again, so we'll set the default value for gamma to 1, which means we care equally for the immediate reward and the later rewards, because in the particular case of blackjack, it's not very long. The episodes are not very long. There's not a lot of different time steps here. They're very short. So we want to here set a value of 1 as a default value for that. So first of all, we want the sum of the returns here. So for a given state action pair, the sum of the returns. So we want to store that in its own dictionary. So we want a default dictionary so we don't get any exceptions if the key is not found. So we're just going to create that entry in the dictionary, and we'll initialize it here with a lambda and p.zeros for the dimensionality of the action space. So there's only 2 actions here. Okay, and we want to do the same thing. So we want n. So for every time that we visit a particular state action pair, we want to record that for every visit, because we're doing every visit Monte Carlo. And then we want our Q table, which again is just the same thing. It's just an empty dictionary and default dictionary. And we'll as we loop through, as we collect episodes, we'll go ahead and fill all of these in. And let's just jump right to it so you see how that works. So we are going to loop through episodes in the range from 1 to our number of episodes plus 1. So let's say we pass 100,000 episodes, then we're going to loop through that many and update here our dictionaries that many times. Now, for every 1,000 episodes, we actually want to print our progress. So we're basically going to print our episode, which one it is, what are the total number of episodes, just a ratio there, so we see our progress. And then that's why we imported sys, because we want system. So sys.std out.flush, and that's going to basically be printing our output here, and you can see how you'll see in a moment how that works. But we already ran these cells, of course, to save time, so we can just run and learn along. Okay, so we're just going to be monitoring our progress, and then we're going to generate an episode. So we create an episode variable here, and we have our generate episode function that we passed in here into our Monte Carlo prediction function, and we're just going to pass in our environment as we saw before. So it's this right here. So that's how we're going to be generating episodes. Okay, so we have an episode here, and then we're going to obtain the states, actions, and rewards. So we have our episode, and then we're going to zip all the corresponding values. So all of the states are going to be zipped together, the actions and the rewards, everything is going to be zipped together. So we have all of the states, all of the actions, and all of the rewards for any given particular episode. Okay, now we want to also take into account discounting. So the way we do discounting, so think for any given state action, for any given state, you took an action and then you got a return. So it's the sum of all of the rewards by following the policy from there, essentially. So think of it as a power series. So the first term and the rewards, you want to multiply it by gamma, by this factor, to the power of I. So I being in the range and for the length of the rewards here. So for example, let's say the gamma is 1 in this case. So we want to raise it to the power of I here. So 0, 1, 2, and so on for all of the rewards, for the length of our rewards here. So if gamma is anything between 0 and 1, then because you're raising it to the power of I, and I is going from 0, 1, 2, 3, this number is getting smaller and smaller and smaller. So later, as you progress, so the later rewards get less of a weight and less of an importance, basically decaying, and you're only the more immediate ones get the most value. Now, if it's 0 gamma, so this gamma is 0, then only the first one really matters. So we're going to just create a numpy array from all of our gamma to the ith power, and each of our rewards, in a moment you'll see how each one will be multiplied by this gamma factor. And again, think of it as a power series where each return, each cumulative reward is for any given state and an action, you're going to be multiplying that gamma factor here. This is the discounted return, we call it. Okay, so for I state and enumerate states, so we have our states and we're going to go ahead and enumerate them. So we have a return sum dictionary that we have before. So for the particular state here, we're going to go ahead and grab the actions at I. So that's why we enumerate. So we can actually grab, so for the given state, we grab the corresponding action that was taken in that state, and then either add it or assign it there to that entry in this returns and the sum, in this return sum dictionary, where we have the sum of all the rewards. So we're going to assign the sum of the rewards, so going from I, for wherever we are, up until the end, and those rewards, and then we're going to multiply this array here by the discounts. And now the discounts, we don't want to start with the discounts. So if you have your rewards here starting at I, you want to grab your gamma, you want to stop. So you have a full NumPy array here of all the discount rates. But all these rewards may not be all of them unless you're at the very, very first I here, which is 0. Then you have all of them. Then you want to multiply all of them, all of the rewards by all of the discounts. So, and that happens element wise. So the first element is multiplied of the rewards is multiplied by the first element of the discounts, and so on. But now let's say you're at 1. You're at the next. You're looping through these states. So you're at the next one. So it's 1. So now the rewards, you're not starting at the first one. You're starting at the second one and going all the way to the end. So for the discounts, you don't want to grab all of them. You want to grab all of them minus the last one, and then you just kind of keep removing elements from the discounts from the end, and then this and as the rewards get more into the reward, so to speak, right? So as you're starting more into the list, further along into the list, you want to cut off the rewards correspondingly before the end, because these have to match. I hope that makes sense. I mean, also feel free to just pause here and just go through it on your own, and I'll post a link also, to all of this code at the in the description. So also for each state here, we also want to record the visit to that state. So for that particular state and that particular action, we want to just assign equals 1 here. So just we want to record the visit to that state. And then for our actual queue table that we're building, so for our state, for a given state, we took a certain action, so we have the action taken in that state. We want to actually assign the return, so the sum of the rewards here, so the return sum dictionary here. So for that particular state, for those actions, so just the corresponding ones, and then we're going to divide that by the visits to that state, because we're doing every visit Monte Carlo, so we want to average out the visits. If there's multiple visits to that pair, we want to average out. Otherwise, this will just be we'll just be dividing by 1, and it won't really matter. But we're just grabbing the average return or cumulative reward here. So we're going to go ahead and loop through that for all of the states for every episode. And then at the very, very end, once we loop through all of our episodes and we have all of that, we're going to just return this queue table. And the more episodes we choose, and this is a hyperparameter, the number of episodes, think of it as epochs. And that's the closest we'll be to the action value function, which is what we want. So now here we're going to use this cell here to obtain the action value function estimate Q. So again, that's what we're returning. So we'll just go ahead and assign that value. So Monte Carlo prediction, MC underscore prediction underscore Q, this function that we have here. And then we pass our OpenAI Gym environment instance. Then here we're doing it with 500,000 episodes, 500,000 episodes. And then we just pass the function that we created before, generate episode from limit stochastic, right? Which is our function that we have here for generating episodes with this random policy. Okay, so we have that, and now, so that's an approximation to the action value function. Now we want to grab now, for plotting purposes, the state value function. So we just want to average out the returns for both of the states that we had here. So here for Q is a dictionary, as we saw before. So for K, for key value and Q.items, so that's how we're going to loop through our dictionary. We're going to grab the item. So K is the environment state. And remember, that's a 3 tuple. And then V is the return for each of the 2 possible actions in that state. So it's a list of 2 values. So the return for having taken the value stick, which is not draw a card, and the other value for having taken the action 1, which means draw a card. So we have those, and we're just going to do a numpy here, just a vector multiplication here with that, and with the corresponding probability. So if the environment state, the 0th index, which means the player's current sum, the agent's sum is greater than 18, then we want to just multiply that by this here, np.dot, so the dot product of these 2 values, as we saw before, right? These are the rules for our environment. And we want to do it, and for 2 possible actions, and that's a number, right? This dot product returns just a number. That's basically the average return for those two actions in that particular state. So we have that, and then we just want to go ahead and add that as combine that, so add it to the other possibility. So when the agent's current sum is less than or equal to 18, we just flip the probabilities, right? Just do the dot product for the corresponding actions or the returns for those actions. And now we get that value. So again, it may be a little confusing initially, but again, feel free to pause and just look at it at your own pace. And I'll also post all of this in the description. Okay, so that gives us a dictionary of which are the values to plot. So we store it here in a variable that we call v_to_plot, and then we're going to just call our function that we imported initially from our utils script, plot blackjack values, and we'll just go ahead and pass in that dictionary. So we're plotting the state value function, so we can see what that looks like for the blackjack environment. So it's very interesting. So you see here we're plotting the player's current sum on one axis, and then the dealer's showing card. Remember, the dealer has a face-up card and a face-down card. So this is the face-up card, and then the value of the state. So the average out having averaged out and take into account the two possible actions in that given state, though that's just the net return or cumulative reward for the agent. Okay, and then we have two plots here, whether we have a usable ace and whether we don't have a usable ace. So they're very similar plots here, and as you can see here, unsurprisingly, the return or the cumulative reward that the agent receives is highest here. It's highest whenever the agent's current sum is closest to 21, and then as you go back, then the return decreases, and it's pretty flat under 18, or pretty much the same. I mean, there's still variation, but this is just intuitive. So the closer the player's current sum is to 21, the better the chance, the higher the return, because it was the higher probability that the agent will not have drawn a card, right? Because if you're over 18, our random policy had an 80% probability of not drawing a card, and then a 20% probability of actually drawing a card. So this is just a plot to show you kind of the distribution and how that works, the returns based on these parameters. You just feel free to look at it on your own, but it's also pretty intuitive. And again, here another thing to note is that it doesn't matter what the player's mostly it doesn't matter what the player's current sum is. Like, for example, if it's if it's 21, it's always receiving the maximum reward here, independent of the dealer's showing card. So it's very, very interesting. So that's it. So that's an basic introduction to Monte Carlo methods and reinforcement learning. In other words, using random policies for creating an agent that learns to play the game of blackjack. And it's just very nice to see. So thank you for watching. Now, in the next tutorials, we'll go into more sophisticated ways of improving these Monte Carlo methods and these random policies, particularly using greedy policies and epsilon greedy policies. But we'll get into that, and you'll see how powerful that is. So if you have any questions, thoughts, comment below, or if there's anything that in particular that you want me to cover, also let me know in the comments. And again, if you haven't subscribed, go ahead and hit the subscribe button now, and I will see you next time.